In this video, we'll look at electron configurations. We've seen previously how to draw electron orbital diagrams, but it's really cumbersome to draw a bunch of boxes and arrows everywhere. It's a little easier to write an electron configuration so that we can quickly and easily convey to each other where the electrons are, what orbitals they're in, and how many electrons are in that particular orbital. So this is a way we can describe and show the distribution of all of our electrons in an atom. Each component is given a number for the energy level, a letter for the type of orbital, and a superscript to let us know how many electrons there are. So if we remember our electron configuration shorthand that we saw briefly before, the N, that's the principal quantum number, that's the orbital we're in, or that's the energy level we're in. The letter L, the magnetic quantum number, that's when we write our S, P, D, or F. And then the superscript, that's the number of electrons in that subshell. So we can see designated here, the number denotes the energy level, that'd be 4. For 2, the letter tells us the type of orbital, that's P, so this happens to be a 4p orbital. And the superscript tells us how many there are. So that happens to be 5 electrons in our 4p orbital. Pretty straightforward, right? So as long as we know the total number of electrons possible in each orbital, we can easily write electron configurations. And so when we're writing our electron configuration, instead of drawing a box and an arrow out for a 1s, 2s, 2p, 3s, 3p, 4s, 3d6, we saw that last time, took a while to draw it out. Now we can just write out 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d6. That's the exact same thing as if we drew out our boxes for our 1s, our 2s, our 2p, and then so on and so on. 3s, going to run out of room. We continue on. But you can see the number of arrows you draw, that's our superscript. So instead of drawing 6 arrows, I just write the number 6. Or instead of drawing 2 arrows, I just write the number 2. Pretty easy and straightforward, right? But then this also becomes kind of cumbersome, particularly when we get down to some of the heavier atoms. If we were to write the electron configuration for something like gold, Au, gold has 79 electrons. Trying to write this out for 79 electrons, that would take some time. But instead, we can also use a shorthand. So notice how iron has the same first set of electrons as argon. It has the same electron configuration here as argon. See, highlighted in red for you guys. The only thing that's different, so you can see iron and argon, they have the same electron configuration here. And then iron starts on the next level down on the periodic table, it's the next row. That's when we start filling in the 4s and then the 3d. And then we'd fill in the 4p after that. But you can see the first 3 rows of the periodic table, iron and argon are the exact same. So this is what we call the noble gas configuration, noble gas shorthand. So instead of writing the entire thing out here, I can just write argon in brackets and then the rest of the iron configuration. Makes it a whole lot quicker to write out our configurations now if we use the shorthand notation. So let's practice this and let's look at this a couple ways. When we're writing our electron configuration, we can do the 2 ways. So if I write the electron configuration out for carbon, carbon has 6 electrons. So it's really not too bad. I can write 1s2, 2s2, 2p2. Or if I wanted to write the shorthand, I can write helium, whatever the previous noble gas is. Always use the previous noble gas. That goes in brackets, and then you continue on. So helium is a 1s2. And then carbon is the next row after helium. So that's where you get the 2s2 and 2p2. Not super useful for carbon because it only has 6 electrons, but something like mercury. Mercury is element 80. Trying to write out 80 of them, that's going to take you guys some time. But if we look at mercury, the xenon is the noble gas right before that. So since xenon's the noble gas right before that, I can write xenon in brackets. And xenon in brackets represents everything through here. So all of that is the exact same as writing xenon. And one quick note, the 6s2 here should be in front. Slight typo I see on my slide. 6s2 should be in front here. And then you have the 4f14, 5d10. So it should be 6s2, 4f14, 5d10. Let's make a note of that, everybody. So you can see writing the noble gas configuration makes it so much simpler when we get to the heavier atoms. So much easier. So remember, it's always the last noble gas before your element. So look at the last noble gas before the element. And then that'll go in brackets, and then you continue on. So you have to make sure you know or have a good idea what the configuration is for that noble gas. Got to make sure you know which orbitals you're filling up. So for that, if you remember, if you're ever unsure, you can remember the diagram I had about the different orbitals, where they're located. On our periodic table, quick periodic table for you guys. This is the s orbitals. These are the d's, these are p's, and these are f's. And then the different energy levels. You start 1, 2, 3, 4, 5, 6, 7. Remember, D has to start at 3. So 3D is your first one. And then 4F is your first F orbital. It's important to remember which ones are the first possible ones to start with. Remember, you can't have a 2D. You have to start with 3D. And then the electrons we write inside the brackets, those are what we consider the core electrons. Those are the inner shell electrons. They're usually considered core electrons because we filled up to that noble gas level, so that becomes a much more stable configuration. Any electron after that is what we call a valence or an outer shell electron. And we'll get more into that later. So looking at how our orbital diagrams and electron configurations relate to each other. If I have sodium, I have a 3s. The full electron configuration for sodium would look like this: 1s2, 2s2, 2p6, 3s1. Or if I write the condensed configuration or noble gas configuration, that would be neon, 3s1. And same thing with magnesium. Magnesium fills up 2 electrons in the 3s orbital. Magnesium fills up 2 electrons in the 3s orbital. So that means it's a 1s2, 2s2, 2p6, 3s2, or neon, 3s2. So you can also see the building up principle where we're adding 1 electron each time when we move over 1 atom. And then we're always adding it to the next energy level. And you can also see Hund's rule applying here, where we add electrons into the empty orbital first. So you can see we're adding into the empty orbital before we start to pair up electrons. Once we have no more empty orbitals, that's when we start to pair up our electrons till we get to what would be considered the next noble gas, argon. And so even with argon, we have our core electrons here, and then we have 8 outer shell electrons. So you can have neon, and then 3s2, 3p6. it's completely filled, but they're still considered outer shell because I haven't moved past that noble gas. And so you can see what I mean by that. If we look at neon, I'd have helium 2s2, 2p6, or argon would be neon 3s2, 3p6. But here's the electron configuration for some of the early atoms in the periodic table. You can see for each one, we're adding one electron each time because if we remember when we're figuring out the number of electrons for a neutral atom, that's the same thing as the number up here, same thing as the number of protons. So since we're adding one proton each time, we're adding one electron each time. And you can see when we're looking at the columns, the outer shell electrons are the same going down the column. We've just changed the energy level. So nitrogen is a 2s2, 2p3. Phosphorus, right underneath that, is a 3s2, 3p3. So you can see it has the same configuration. It's just the next level up, or the next level away from the nucleus. This is how atoms in the same column start to experience similar chemical behavior. So example, if we look at the halogens, all the halogens have similar behavior to each other because you can see they have a similar outer shell electron configuration or same valence electron configuration. So that's why if we remember each of the halogens, when it forms a charge, forms a -1. You can see if it forms a -1, now it has the same number of electrons as that noble gas. Now, this wouldn't be chemistry without some exceptions. A couple exceptions is sometimes if we allow the half or full shells to occur, those are always more stable. And if we remember, the 4s and the 3d are very close in energy. So sometimes electrons, instead of going into the 4s, actually go into the 3d. As you can see, the ones highlighted here in yellow, those are our exceptions. They tend to have an electron jump from their 4s or their 5s into the respective d orbital. And you can also see with the f orbitals, those have a lot of exceptions as well. And it's that same idea occurring, where if I move just one electron, I can create a full shell or half shell, and that makes a much more stable configuration. And so if we're looking at writing our electron configurations, here's some practice. If we want to write the full configuration and the condensed one, pause the video, try and write it on your own, and then unpause the video. Okay, now when we look at our configuration for beryllium, hopefully everybody can get this, the full configuration, 1s2, 2s2. The condensed one, or the noble gas configuration, helium, 2s2. So now looking at arsenic, arsenic is element 33. We can see that goes to the 4p3. Or if we write the noble gas, that's argon, 4s2, 3d10, 4p3. Now finally looking at copper. Copper, if we remember, was one of our exceptions. The exception for copper is one electron jumps from the 4s orbital over to the 3d. So copper without that exception would have been argon, 4s2, 3d9. So you can see if I just take one electron from that 4s and move it over to the 3d, I've filled up that entire 3d subshell, which makes it slightly more stable of a configuration, having just that one unpaired electron in the 4s orbital. Because remember, there's only one box for the 4s. For the Ds, there's 5 boxes. I filled all 5 of those up. That stabilized it a little bit more. So this is typically what happens with our exceptions, is they'll jump from the 4s or whichever s orbital into the next d orbital. So if you remember, copper is one of our exceptions. If we followed the expected, it would have looked like that. So now looking at electron configurations for a monatomic ions. So whenever we create an ion, this is where I kept telling you they need to get the same number of electrons as the noble gas. Remember that from earlier. Sodium, if sodium loses one electron, it's going to lose it from the highest energy orbital, that 3s. So if it loses an electron from the 3s, it forms a sodium plus. Sodium plus has exact same electron configuration you see as neon. And so when we're looking at our metals, when they lose electrons, they tend to want to try and create something with a similar electron configuration to noble gas. And this is what we say is isoelectric. They have the same electronic configuration, so we call it isoelectric. Bromine has an electron configuration where if I add one more electron and create bromine with a negative charge, that has the same configuration as krypton. So it becomes isoelectric with krypton. That's its nearest noble gas. So this is why in the beginning I told you these elements in the main groups wanted to form wanted the same number of electron as the nearest noble gas. This is why. This way, they have the same electron configuration. They have that same stability that noble gases have because they filled up their shells and they don't have any electrons in the next shell. So now you guys should be able to write your electron configurations for your neutral atoms and for your ions, for the main group ions.